Hello, this is Mrs. Rutchling, and today we're going to talk about scatter plots. These are the graphs that we're going to use most often in chemistry, and they show us the relationship between our independent and our dependent variable. We can look at it for trends. If we needed to, we could calculate the slope, and that would represent our rate of change. We use graphs because a lot of times a table of numbers is very difficult to interpret. If we look at a graph, we can see our trends, and then we can also look beyond our individual data points. We can extrapolate, meaning we can use the same slope above or below the measured data. So if we have 2 points here that are measured, we can extend the line and determine the ordered pair for point D. That's extrapolation. Here's a nice view of the red line is our line of best fit for our graph data. Extrapolation would be anything beyond that data. So over here above about 42, and on the left hand side below about 10. We can also interpolate, right? And that inter means in between. And so we can use our slope or our line of best fit to figure out where the point should be in between. Okay? And again, if we go over to the graph here, if we're going to look at data points in between our measured data points, it would be here on this red line. Let's look at some guidelines for creating a scatter plot that will help you be successful. We're going to be drawing graphs all year, and every graph should give some sort of title that's going to give a description. We should be able to determine the labels of the variables. You don't want something very simple. If I'm looking at pennies, I don't want the graph to just say pennies or pennies graph. I want it to say something about the correlation between the number of pennies and their mass. There's some examples there. The dependence of dependent on independent, the dependence of y on x, or the effect of x on y. Sometimes you're going to need to put a key to explain some symbols. This will be especially useful when we're graphing more than one line on the same graph. Always on graph paper. Luckily, our lab notebooks are graph paper, and if you need to write one in OneNote, you can get graph backgrounds. It's important to use a straight edge. So you can use anything. That we have plenty of rulers available. If you're making an electronic drawing, again, maybe in OneNote, use the line tool. The axes should give you a label, so mass of pennies, and a unit, grams. We always put the independent variable on the x-axis and the dependent variable on the y-axis. The only exception is time. If time, when we're graphing time in chemistry, it will always go on the x-axis. So one of the things when you're drawing a graph is that the graph should fill up the available space. So when you're going to draw a graph, it should take up at least half of the page. When I grade your labs, I'm going to fold it over and see if it's approximately half of the page. All right? And if it is not, you're going to see some marks. So for example, this first graph, you would see me draw this, meaning expand it. The second one, we want to make sure that the graph is filled with the data. We don't want empty space. And so you may see a mark like this when I'm grading. Okay. The third one on the right here is about half the page, and the data fills the space. Okay. And so that would be an acceptable graph. Each axes can be different, but within an axis, it needs to be consistent. So if one box equals 10 minutes at the beginning, it has to represent 10 minutes throughout the graph. The range is going to be different. So if we look at this example, the range here is time from 0 to 400 seconds. But if we look at the y-axis, we have 1 times 10 to the negative third mole per liter to 5 times 10 to the negative third. Okay. So notice that each square is 1 times 10 to the negative third here, and each line is 10 and each square is 100. That's true here where we start, and that's also true when we go from 3 to 400. You'll notice that the scale for the y-axis here doesn't start at 0. Many times it's not going to. Right? You want to choose a scale that's going to fill your graph. If I started here at 0, there would be a large blank space and all of my data would be in one area. So I've chosen a scale that spreads my data points across the whole graph. Similarly, I've done this here for the time in seconds. The scale doesn't go to 800 and my data stops at 400. I've stretched it out so that from 0 to 400, because that's where I have my data points, goes all the way across the bottom of the axes. It's usually easier to make your graph and to actually read it when each square or each line represents an increment of 1, 2, 5, or some multiple of those. You want to label your axes at every regular interval. Doesn't mean that you have to do every square on graph paper, maybe every 5, whatever works, but you do want to be able to check out the data of your ordered pairs by easily looking at your axes. And then again, remember that every axis should have a label. So here we have time, and the unit is in seconds. Over here we have something concentration, phenolphthalein concentration, that's the label, and then the unit is mol/L. Chapter 2, we're going to be looking at significant figures. Once we know how many decimal places a number should have from our data, that should match on your graph. And we'll talk a little bit more about this when we get to significant figures. We'll be drawing best fit lines, or sometimes they're curves. It's important to remember we will not be connecting the dots. Now, these are experiments, measurements, and so they're not all going to fall on a line or perhaps a curve. In math class, sometimes that happens, maybe even in physics, but in chemistry it usually doesn't. So you want to draw a straight line that best represents the tendency of the data points. This line of best fit does not have to go through the origin. That's different than perhaps some things you look at in, again, math and physics, but many times it will not go through the origin in chemistry. So we want to take our line of best fit. Notice I'm using a straight line, and you put it on here, and you want to have it go from the beginning to the end of the points. You don't want to extend it beyond, because we don't really know what the data does here, and we don't put arrows because we don't know. Perhaps whatever this data is levels off here, and so putting an arrow would be misleading. Now when I place this line on the graph, I try to position it so that I'm hitting some of the points, although sometimes you may not, but you want an even amount or a similar amount of points above and below. Here I have 2 and 2 below, and so that works. Here are some examples of lines of best fit. Okay, so see, this one does not go through the origin. We stop it on both sides of our data. We have a couple of points above and below. Here's another similar one. This one actually goes through 0, or it appears to, but again, we don't extend it past the data points. Here are some curves. Curves will be a little more unusual for us, and if I expect a curve, I would tell you that the line of best fit would be a curve. So this is one type, and here's another. Here's some graphs that show the effect of scale on how we interpret it. This is the same data, two graphs of the same cell phone use data. Here we've spread it apart, spread the data out throughout the graph, and here we have started from 0, and most of our data is in the first two data points. While this kind of graph has its uses, in chemistry we're going to be wanting to look very closely at the changes over time and looking at our trends, so we will want to stretch it out. Here's another set of graphs. Data is the same on both of them. Here the data is scrunched together, and here it is spread apart. So what we want to see is something that looks like this. If you turn in a graph like this, I'm going to take off points and it'll look like that when you get it back. On this page we see some common mistakes. One of the problems, especially on the first two graphs, are there is no title, there is no labels or units on these two graphs, so we have no idea of what it is. This one's a little bit better. We have late coming occurrences in school. However, it doesn't really tell us what we're looking at, and we wanted to say something about the months and the number of students who were late. If we look at our first graph, one thing I noticed right off the bat is that the points are connected instead of a line of best fit, so that's a problem. If I look at my scale on my x-axis, it's nice. Every square represents 1. But I do detect a problem here on the y-axis. So here I have one, but then all of a sudden the same space represents 2, and then 4. Okay, so that's a problem. I also see here, and this is a common mistake, where the students have just plotted the data points instead of creating a scale. Right? So I have from 0 to 5 is 5, from 5 to 10. All of a sudden the same space is worth 10, and then again 5, and then 2. Right? So we need to not take the data and put the points there, but make a scale that encompasses it. This graph is not bad. It does have the 5, 10, but all of a sudden, once again, 5, and this is equal to 10. And so you'll see me mark this and you know your scale is off. When we're looking at the relationship between the variables, we can say that this is a direct relationship in both of these graphs, as our independent variable increases, our dependent variable increases as well. This is also called a positive correlation in your math classes. An inverse, or sometimes called indirect relationship, is when one variable increases, the other decreases. It's going to give you a negative slope, and it's often called a negative correlation. Okay, so these two both show indirect. As I increase the pressure, the wind speed decreases. Here, as I increase the temperature, the pressure decreases. I often hear students say proportional, so I wanted to talk a little bit about what that means. When we're talking about a direct proportional or a positive proportional relationship, the ratio of the two variables gives a constant number. Or you can say that if I take x and multiply it by a constant, it's going to give me y. You may be familiar with this if you look at a linear relationship. You may recognize this if you have a equation for your line, and this linear relationship is going to go through the origin. This really isn't that common in chemistry, right? So we have a positive or a direct relationship here, but this one is proportional because it goes through the 0, and you can see that I take 0 sandwiches times 250, that's going to give me 0. I take 2 sandwiches and multiply it by 250, that's going to give me 5, etc. So I get my straight line, I get my equation, and my line goes through the origin. An indirect proportional relationship has one variable decreasing as the same rate as the other one increases, and it makes a hyperbola. Mathematically, it looks like that, but we don't have to worry about that quite yet. Let's try some practice. We're going to look first at some data and try to decide if they are proportional. So if they're proportional, if I take hours and multiply it by something, I will get the number of miles, and that would be consistent. So one way to quickly check that is to divide the miles by the hours. And if I do that, each time I get 65. So yes, this one is proportional. If I look at pounds and the cost, if I do the same thing, again, I get a multiplier that's the same. So yes, this one is proportional as well. Lastly, miles per hour. I plug in my values. Now notice that I don't put in fractions because typically we do not use fractions in chemistry, so get used to using decimals. You can't measure anything in fractions using our tools in chemistry, so we don't use that. But once again, when I plug these values in, I get a consistent multiplier, so C is also proportional. Going down to the next set, I want to see if they are direct or indirect, and then also if they are, I want to know if they're proportional or not proportional. Well, I can see that this one is direct because as I increase x, y increases. However, it is not proportional because the line of best fit does not go through 0. Looking at my second graph, I have a negative slope, so that's indirect, and it is not a hyperbola, so it is not proportional. My third graph has a positive slope, so it is direct, and it goes through the origin, so it is proportional. Lastly, I have an indirect or a negative relationship here, and it is a nice hyperbola, so it is proportional. Lastly, I'm going to look at how I'm going to grade your graphs. Okay, this is a sample rubric for a graph, and it tells us all of the things we've talked about. Our title includes dependent and independent. How is the axes labeled? Can I see the units and the label, and is it evenly spaced across? Same thing for the Y. Does the graph take up half of the page, and does the data fill the graph? And then, did you do it correctly? Did you draw the line of best fit? And did you not connect them but draw your line of best fit? So when I'm grading at the beginning here, just looking at the graph, I'm going to use this. Later on, when we're including the graph as part of a larger lab report, it's all going to be combined here, and it's going to have similar wording. Does it have the right scale? Does it have units, title? Does it fill the space? So does that mean, does the data fill the graph? Is it appropriate in size, half the page? Do you have your independent variable on the x-axis, and is your line of best fit drawn? I hope this helps your understanding of what's required to be successful making a graph in chemistry class. Thank you.